Today we enter the arcane world of modeling, that is, computer modeling of climate. This video segment hopes to provide some understanding about this approach, which remains the best one for predicting the future of Earth's climate. The major points of the segment are: number one, models are necessary to study processes that are too slow, too large, or too unique for direct observations. Number two, global climate models, GCMs, exploit all the computer power available. Number three, global climate models are based on relatively simple laws from the physical sciences. Number four, global climate models take two major approaches for solving the equations that describe changes in weather over time and space: the finite differences approach and the spectral transforms approach. Prophecy can be challenging, be it predicting the stock market, betting on horse races, or forecasting weather or climate. Consider differences between weather and climate forecasting. Weather forecasting has a day-to-day and town-by-town focus, whereas climate forecasting takes a broader perspective. For example, TV weather reporters each evening must address the question, should you carry an umbrella to work tomorrow? Whereas climatologists may spend their entire career pondering, will Manhattan and the rest of the North Atlantic coast freeze solid during the coming decades? Indeed, climatic forcing factors discussed in previous segments range from cosmic, spinning around the galaxy, to mundane, driving to work. Have climate forecasters gained sufficient insight into the mysteries of the universe to predict Earth's climate with any accuracy? One impediment to accurate climate forecasting is that many important forcing factors are A, so slow, B, so large, C, so unapproachable, or D, so precious as to preclude direct experimentation. Study of such phenomena requires the development of facsimiles that are A, shorter in duration, B, smaller in size, C, more accessible, or D, less unique than the original. These facsimile or models may be physical entities or mathematical abstractions. Physical models are common. They include playthings such as dolls and toy trucks that mimic the functions of their full-size counterparts. Other physical models require additional adult supervision. For example, the Boeing company conducts tests on replicas of their new airliners in large wind tunnels to simulate the airplane's performance under extreme conditions. When emulating the details of a complex system in a physical model becomes difficult, mathematical models may supplement or replace physical models. The wind tunnel tests on new Boeing airliners are tightly integrated with mathematical models calculated on computers. Climate models have undergone a similar transition from physical to mathematical. Early studies of atmospheric and oceanic circulation patterns example simple physical models. Sometimes a container filled with fluid was placed on a hot plate that represented the warming of the tropics, where cooler areas of the container represented the poles. In more elaborate physical models, a heated tank was mounted on a turntable to mimic Earth rotation and the Coriolis force. These efforts became known as General Circulation Models, or GCMs.